So another question we want to discuss today is what actually does MATLAB's ODE45 do? Like we know it's a Runge-Kutta type of method, right? But we haven't even discussed the Runge-Kutta type of method before. So in ODE solvers, the only type of method we discussed before is called either a one-step method or multi-step method. So that is basically saying that for every time step, I'm evaluating the same formula for computing what's the next step. But in reality, I don't have to do that. And also for multi-step method, I'm not doing that anyway when I start, right? So for example, if we use the simplest multi-step method, which is what we derived the first day of the class, the midpoint rule, we would have to say my un plus 1 is equal to un minus 1, minus 1, not minus 2, plus 2 delta t times f of un. But since when n is equal to 0, we don't have un minus 1, so we have to start with something. So that is only true for n greater than 0, right? And for n equal to 0, we usually use the forward order. So u of 1 is equal to u of 0, our initial condition, plus delta t times f of u0. So a natural question is, why don't we just use these two methods alternatively? Right? Why don't we just use one step of forward order, another step of midpoint rule, and another step of forward order, and another step of midpoint rule? So if we do that, what is the order of accuracy you would expect? The order of accuracy of the largest
like the largest order of accuracy.
The largest order of accuracy, why is that? The smallest, why is that?
Because the delta t term dominates for small delta t.
That's also what intuition I would have. So usually if you mix a high order scheme and a low order scheme, what you get is the behavior of the low order scheme. Right? Because basically what you get is you have a term that is order delta t, you have another term that is order delta t squared. Ultimately, if you add them together, is the term that is O delta t that is dominant, right? The O delta t squared is so small that it doesn't really matter. So usually when you mix a high and low order scheme, it becomes a low order scheme. But this is a very interesting exception. It turns out in this particular case, if you mix a first order scheme with a second order scheme, you somehow magically get a second order scheme. That's not always the case. And that kind of promoted people to look at, okay, so what if I mix different low and high order schemes? How do I use this kind of a magic mixtures to get high order schemes? So let's, for example, analyze in this case. So if we have if we turn this into a alternating scheme, and we say, okay, so for every, let's say for every odd time steps, u of 2n plus 1 is equal to u of 2n plus delta t times f of u2n. So for the odd time steps, when I'm trying to go from an even to an odd, I use forward order. And when I go from odd back to even, I use midpoint. Okay, so how do I show that I can get a second order scheme? Still Taylor series analysis, right? The whole thing, up to now, I haven't really taught you anything new. You knew how to do Taylor series analysis. You know how to do eigenvalue analysis of a matrix, right? I'm just using these two tools in all kinds of situations to show accuracy and stability, which is the two things that are very important, together with how much computation time you have to spend on your computer. These are the three things that are really important for numerical methods. So if you do that, if you do Taylor series analysis, let's see what do we get. So if we perform these two schemes, we can compute, okay, so what is u of 2n plus 2 minus u of 2n? If you take the difference, we'll get 2 delta t of f of u 2n plus 1, right? Okay, so that's the numerical formula. But is this the right way to do accuracy analysis? What's the right way to do accuracy analysis? Taylor series, but how do I start?
Expand u of 2n plus 2.
Well, the first thing to start is to look at our numerical formula and realize that these are only exactly equal if you put hats on it. All right? Okay, they are not going to be exactly equal if you plug in the true analytical solution, which is the only thing you can use to do Taylor series analysis. I mean, for the numerical u, the numerical solution only exists at discrete time steps. They don't exist as continuous functions. Only the true solution, analytical solution, they exist as a function of a continuous variable t, and therefore is able to do Taylor series analysis. Right, so always remember, when you do Taylor series analysis, you are not going to be doing this with the exact formula. It's only approximately equal, right? So this is 2 delta t times what am I doing here? So this is f evaluated at right. So okay. So let's expand Taylor series analysis on these two terms. So the first term is u of 2n plus 2 is equal to u of 2n plus 1 plus delta t times du dt at 2n plus 1 plus half of delta t squared plus the second derivative at 2n plus 1, right? And my u of 2n is equal to u of 2n plus 1 minus delta t times the same thing. And all of these are added with a third order term. Okay. Now when you plug so that's why if you plug in the same formula into the numerical formula, what you're gonna get is u of 2n plus 2 would be equal to u of 2n, okay, plus 2 delta t times du dt at 2n plus 1. And then I would add this term, actually this term cancels out, I would add O delta t cube.